Okay, we just finished chapter 13 in the statistics textbook. Right now we're going through part 4 of the textbook, which is on probability. In this video, we're going to start chapter 14. We're going to go through the first section. Chapter 14, you can see, is titled More About Chance. So all we're doing in chapter 14 is just a continuation of the same types of topics we were doing in chapter 13. So in chapter 13, we learned about the meaning of probability and chance, specifically from the perspective of frequency theory. Okay, and then what we mainly learned was that any probability problem, if you're trying to solve for a probability, all you really need is to know how to count, how to count really well, because any probability problem can be boiled down to just a single fraction bar and then two separate counting problems. One, you want to count the total number of outcomes in general for the probability question you're asked. So that would be like, you could think about that as like the total number of outcomes in the entire system. And then in the numerator, you treat this like a separate counting problem, but it is related to the count in the numerator, because the count in the count in the denominator, because the count in the numerator is going to be a subset of the system, some subset number of events of the whole system. Okay, and we in the marathon of counting example problem videos, we solved problems, both the big picture counting problems and subsystem counting problems. We solved all kinds of problems from both of these perspectives, just never in the same problem itself. And so now with probability calculations, all we're doing is just solving these two separate counting problems in the same problem and getting this probability ratio. That's it. Okay, and so now that didn't mean that everything we were doing in chapter 13 was totally easy, because we still needed to learn different definitions related to probability, terms, how to classify certain probability scenarios. So the meaning of conditional probability, the meaning of independence and dependence between events. Okay, but when it came to actual probability calculation techniques like the multiplication rule, we were just able to derive the multiplication rule from our counting skills. Okay, so again, when it came to actually calculating probabilities, that's all about knowing how to count. It's all about knowing how to count. So mainly all we were doing is just learning terms and definitions and how to classify problems related to probability, as well as for probability calculation rules. We just saw how those were a simple extension of our counting techniques. Okay, now we also learned in the last section of the previous chapter, we learned how, so in this course, in this textbook, we're being introduced to probability, which means that the probabilities that we're dealing with are mainly ones that you can imagine, that hypothetical infinite scenario where you're performing this event over and over and over and over again, like flipping a coin or rolling a pair of dice, some sort of a game, some sort of event that you can actually think about hypothetically repeating over and over and over again. But there are probabilities to where that's not something you can do. You can't hypothetically, realistically imagine that event taking place multiple times. Like we looked at a court case here, and probabilities were used. The multiplication rule specifically for probability was used to state how unlikely it was to see it was a black man and a white woman driving a yellow automobile. For everything the witnesses saw in the crime, how unlikely that was. But you have to be careful with these kinds of probabilities, because you can't do that hypothetical infinite scenario. I'm going to take a step back and imagine this crime being repeated over and over and over and over again every day for centuries. You can't say that. There's too many confounding variables there. You can't imagine a crime taking place over and over and over again like you would do with flipping a coin or rolling a dice over and over and over again. You can't really say that. Now, that doesn't mean that you can't use probabilities in this way or analyze probabilities from these kinds of perspectives, but that you can imagine that that's a more advanced statistical analysis to really be able to deal with those kinds of probabilities appropriately. So we're going to touch on these kinds of probabilities as we go through these upcoming chapters, the non-game type probabilities where you can actually, I could imagine going outside and flipping a coin over and over and over again for centuries, doing it an infinite number of times. And as we talked about, it doesn't mean that the coin flipping process has to be perfect. Not at all. Not at all. But you still have to imagine realistically being able to do that. Whereas you can't really say, I'm going to imagine this crime taking place over and over and over again. Well, wait a minute. What are the circumstances of the crime? What happened to lead up to the crime? There's no, you can't really say that, right? We're going to touch on these kinds of probabilities a little bit going forward, but mainly since we're just learning about probability at the moment and chance, the fundamentals, we're going to be focusing on these repeatable game type probabilities. Okay, so now again, in chapter 14, we're continuing with the same kind of theme that we were doing in chapter 13, just learning different definitions and terms related to probability, different probability calculation techniques, and relating those to counting. So in this opening section, listing the ways, this is actually going to be a really simple section for us to go through because we know how to count at a high level. What they're really talking about in this section is the textbook is assuming that whoever's reading this textbook is probably not that good at counting. So what they're doing here is they're really trying to teach you some fundamentals of counting, which we already know how to do though. They're trying to teach you some fundamentals of counting and then at the same time illustrate that whole perspective of a probability problem where you're counting the number of events in the denominator and the numerator. Which again, because we know how to count at such a high level, this is trivial to us. So let's take a look and see what they say. A probabilist is a mathematician who specializes in computing the probabilities of complex events. In the 20th century, two of the leading probabilists were A.N. Kolmogorov from Russia and P. Levi from France. The techniques they developed are beyond the scope of this book, but we can look at more basic methods developed by earlier mathematicians. When trying to figure chances, it is sometimes very helpful to list all the probable ways that a chance process can turn out. And if this is too hard, writing down a few typical ones is a good start. So yeah, what they're talking about here is that if you remember when it came to counting problems, it could be really helpful to list out some of the outcomes. If you're trying to solve a counting problem and you're confused, it could be very helpful to list out some of the outcomes so you can clearly see what you're trying to count. That's very helpful. That's all they're talking about here. This is just a suggestion for solving a counting problem is what they're talking about. Okay, so example 1, 2 dice are thrown. What is the chance of getting a total of 2 spots? Okay, so let's just solve this like it's just a pure counting problem, a 2-part counting problem. So we've got our fraction bar here. Now we need to let's first solve the counting problem for the denominator. What's the total number of outcomes here? You're throwing 2 dice at a time. Okay, what's the total number of outcomes that can result? So if you're confused by this, then just list out some of the outcomes. You could get a 1 and a 3. You could get a 2 and a 5. Right now, can you get like a 5 and a 2? Does that make sense? Well, yeah, this is, to count the total number of outcomes, this would be a permutation with repetition problem, right? We're picking from a group of 1, 2, 3, 4, 5, 6 numbers. We've got these 2 events, but we can have a 1 and a 1, a 2 and a 2. We can repeat numbers. That's fine. So permutation with repetition is just going to be 6 times 6. The number of things you can pick from to the power of the number of events you have. So 6 squared is the total number of outcomes. Okay, now let's solve a separate counting problem. And it's really helpful if you think about the numerator as its own separate counting problem. Like start from scratch. Even though it is related, obviously, to the count in the denominator, still treat it like it's its own separate counting problem. So, okay, what we're deeming to be success is a total of 2 spots. So you add up the number of spots in dice 1 to the number of dice in spot 2, and you get 2. Well, they both need to be the aces. They call these aces. But they both need to be 1. That's the only way you can add the numbers from 2 dice and get 2, because you can't get a 0, right? So there's only one outcome here. And there you go. That's it. That is it. You see? That's all that they're trying to illustrate in this example, They're just trying to show us how to go through the counting process. But we don't need to go through this in detail. We already learned how to count extensively in the previous videos. They're talking about here, you're listing out the dice and the different outcomes you can get. That's what they're talking about. It's a permutation. The total number of events was a permutation with repetition counting problem. Okay, now a pair of dice are thrown. What is the chance of getting a total of 4 spots? Okay, well, we've got, once again, a pair of dice is thrown, so there's 36 total outcomes. But now the chance of getting a total of 4 spots. So, okay, to do this counting problem, this is going to come down to it's a combination with repetition problem. This is a little bit of a more difficult counting problem relative to all the ones we solved. It might seem simple on the surface, but this is a bit more difficult. So we've got, what are the different numbers that are involved to add to 4? Okay, you could get a 1, a 2, and a 3. You might say, what about a 4? Well, no, because you can't get a 0. So it's going to be, these 3 are going to be involved. Okay, and so with the combination with repetition problem, we say that, so here we've got these 2 dice, x1 plus x2. They need to sum to 4. So the number of, you could put any number of dots you want, picking from this group into these bins, as long as they sum to 4. Now, but this is trickier because we have restrictions on x1 and x2. x1 has to be less than or equal to 3 and greater than or equal to 1. And x2 has to be less than or equal to 3 and greater than or equal to 1. Okay, but we solved counting problems just like this. This was more on the difficult end, but we solved counting problems just like this. And if you go through this process, you're going to get that there's 3 total outcomes. Now, you could have counted this manually. Okay, like that's what they did here, but we're going to see an upcoming example where they talk about, what about when you roll 3 dice? But then you can think about, what if you're rolling 4 dice at a time, 5 dice at a time? You just have to solve it. Again, it's going to be a combination with repetition problem with an upper and lower limit on the number of outcomes you can have in each of the bins. Okay, and again, I'm not going to go through how we did this, how we solved the counting problem like this in the counting example problem videos. Go back and take a look if you need. But here they just list these out. You could figure this out manually because it's a 1, 2, and a 3, where you can have a 1 and a 3 and a 1, or a 2 and a 2. There's 3 ways. Okay, what about 3 dice? So that they analyze, let's see, would be a 3-dimensional picture like figure 1 would be a bit much to absorb, but similar reasoning can be used. In the 17th century, Italian gamblers used to bet on the total number of spots rolled with 3 dice. They believed that the chance of rolling a total of 9 ought to equal the chance of rolling a total of 10. For instance, they said one combination with a total of 9 spots is 1 spot on one die, 2 spots on another die, 6 spots on the third die. So this could be abbreviated 1, 2, 6. And so here's the different combinations of numbers to sum to 9. But now for summing to 10, here's the different combinations of numbers. And look, you've got 6 trios, and here you've got 6 trios. So they reason that it should be equally likely to roll with 3 dice to where what you roll all sums to 9, as is all sums to 10. It should be the same number of outcomes. But what they found in experience was that it was more likely to roll a total of 10 than it was a 9. And so they asked Galileo for help, and this is a pure counting problem. The mistake they're making that the Italian gamblers made was that they didn't count the outcomes correctly. That's it. And what they were missing was that the difference is that, so here you've got, for summing to 9, you've got all 3s. But for summing to 10, you don't have any of these trios with the exact same number. Like ideally, if you want more outcomes, you don't want to have all 3 of the same number or even like 2 of the same number. You want to have as many of these be all different numbers as possible, because then you could have it like for 1, 4, and 5. dice 1 is 1, dice 2 is 4, dice 3 is 5. You could have dice 1 be 4, dice 2 be 1, dice 3 be 5. There's different ways you could rearrange this. But like here, dice 1 is 3, dice 2 is 3, dice 3 is 3. That's it. You're not going to count, okay, what if then dice 3 was 3? There's no reordering this. And that's what they show here with a 1, 2, and a 6. Well, you can rearrange this 6 different ways. 3 factorial. Here you can rearrange this 6 different ways. Okay, but then when you start getting duplicates, it's only 3 different ways. And when it's all 3 the same number, it's 1 different way. Well, look, here you've got none of these are all 3 the same number. And I think that's the only difference. Yeah, that's the only difference. And so you get 2 more possible outcomes here for rolling a 10 than you do a 9. Okay, now, but we when it came to counting techniques, we did learn how there are circumstances where maybe there's no closed form solution to the counting problem, like using the counting formulas that we learned. And that doesn't mean you can't solve it. That just means that you need to solve the problem manually, like making a table like this, doing a manual count, solve the counting problem for some smaller values that you can count manually, and then make a formula that matches those manual counts, and then use induction to prove that formula for all integers, higher numbers, like you're rolling 10 dice at a time and whatnot. Prove that formula is valid using induction for all integers. Then that's a more advanced method that you can use to solve a counting problem. But this problem here, they did it manually. I guess Galileo did it manually, but we don't have to solve this problem manually. This is the exact kind of problem this is. You can go verify it yourself. I'm not going to do it here. This is a combination with repetition problem with a lower and upper limit on the number of elements that can go in each bin. This problem here is you'll model it just like this. It's an x1 plus x2 plus x3, and if we're doing 9 first, these need a sum to 9. However, the number of elements in x1, x2, and x3 needs to be less than or equal to, well, definitely greater than or equal to 1, and then less than or equal to, let's see, so it's 6. In this case, we're not summing to like 3 here. Like you could get one of these could be a 6, 6, 2, and a 1, for example. But this was a little more involved. This was one of the more difficult counting problems because, especially with the upper limit, because you had to first make a substitution to account for the lower limit being 1. So that would be x1 prime plus x2 prime plus x3 prime is equal to 6. Okay. Which meant that you updated this to where x1 prime, x2 prime, x3 prime is greater than or less than or equal to 5 and greater than or equal to 0. Okay, so you first got the total count where there's no upper limit. That's what you start by doing. That would be the whole, let's see, you're picking from we're picking from the bins. There's 3 bins and going into 6 slots. And so this is 6 plus 3 is 9. 8, choose 6. That's the total number of outcomes without an upper limit. But then you need to use the A union B union C formula to subtract out the scenarios where just one of the bins has 7 or more in it. Because this count here includes let's see. No, okay, you'd have to subtract out. So for this new problem, you would need to subtract out this 8 choose 6 includes counts where, like, it includes counts like x1 prime is 6, x2 prime is 0, x3 prime is 0. It includes counts where x2 prime is 6, x1 prime is 0, x3 prime is 0. So you need to subtract out those cases because that's not included in here. Okay, if you go through this whole process, you're going to get, for this 9 here, you'd get 25. And then you get here, if you made this 10, you'd get 27. Okay, so let's go through these example problems real quick. Look at figure 1 and make a list of the ways to roll a total of 5 spots. What is the chance of throwing a total of 5 spots with 2 dice? Okay, so we've got, let's see, you could get it's just, okay, x1 plus x2 is equal to 5. So there's going to be 36 outcomes. We know that. All right, x1, we could list these out manually, but I kind of want to show you remind you of the whole combination with repetition problem. X1 plus x2 is equal to 5, but then we need to update this to where, because the lower limit can't be 0. It could be as low as 1. So that's what we did here, right? We said that x1 is equal to x1 prime plus 1, and x2 is equal to x2 prime plus 1. That changes the lower limit to where we have now x1 prime and x2 prime can be 0, which is that works better for the whole combination with repetition problem. But now it's still reflective of the original problem. So now we've got here we don't need an upper limit, because like we can't have a dice with that has more than 6 anyway. So we're picking from 2 bins for 3 slots. So we've got 4 choose 3. So that's 4 factorial over 3 factorial. That's 4. 4 factorial over 3 factorial over 1 factorial. That's 4. So this is 1 in 9. That should be right. So you've got a 2 and a 3, a 3 and a 2. You've got a 4 and a 1, a 1 and a 4, and that is it. 4 outcomes. Okay, so for a small problem like this, you probably just go ahead and do the manual count, but I'm just illustrating that no matter how big this problem would be, we know how to solve this with a closed form combination with repetition technique. Okay, 2 draws are made at random with replacement from the box here, this box of 5 tickets. Draw a picture like figure 1 to represent all possible results. How many are there? What is the chance that the sum of the 2 draws turns out to equal 6? All right, so, I mean, I'm not going to draw a picture. They're just trying to teach you how to count. The outcomes are like, so a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, then a 2 and a 1, a 2 and a 2. This is a permutation with repetition problem with, you're picking 2 tickets at a time. So that's 5 times 5, it's 25. What is the chance that the sum of the 2 draws equals 6? So, okay, I mean, you could do the whole combination with repetition technique, but let's just do this manually. So you could get a 5 and a 1, a 1 and a 5. We're going to count reorderings because the reorderings were included in this count. This was a permutation with repetition problem. You could get a 3 and a 2, a 2 and a 3. So there's 4. No, that's not right. A 3 and a 3. 5 and a 1, 1 and a 5, 3 and a 3, 4 and a 2, 2 and a 4. So 1, 2, 3, 4, there's 5. So what are the chances that they sum to 6? It's 5 and 25, 1 and 5. Okay, a pair of dice is thrown 1,000 times. What total should appear most often? What total should appear least often? So here they're trying to illustrate that whole infinite scenario. If you threw a dice, which, see, you could repeat this. If you could hypothetically repeat this, and it doesn't have to be like this perfect, no event where like there's just, you're throwing the dice on a perfectly flat surface with no wind in a temperature-controlled environment. No. You just go outside and you just keep throwing a dice on the road, whatever, and seeing what turns up on top, and do that for centuries. What's, as the limit of the total number of throws approaches infinity, what's the ratio is going to approach? Which outcome is going to appear most often? Which one's going to appear least often? So which sum of the 2? So it's got to be sevens, right? Because everyone's always trying to get a 7. And the reason why that's going to be the case is because you've got 1, 2, 3, 4, 5, 6, and a 1. Okay, now you've got 1, 2, 3, 4, 5, and a 2. Okay, 1, 2, 3, 4, and a 3. And that's it. So there's 2 here, 2 here, 2 here. Because you could flip these. So that's 6 and 36. That's 1 and 6. But if you do any other sum total, like you say, okay, what about summing to 6? Well, you're going to get a 5 and a 1, a 4 and a 2, and then a 3 and a 3. So that's going to be 5, or no, that's going to be 2, 4. The 3 and the 3 doesn't reorder. That's 5 total. If you try and say, what about summing to 8? Well, you'll have like 2 4s involved, where you only get one possible outcome out of those. So 7's the most likely. Now, the least likely is, so they said here, the total appearing most often is 7. The least likely is going to be a 2 1s and then 2 6s. So that would sum to 2 and to 12, because there's only one way you can roll a 2 or a 12 when they both sum to 2, they both sum to 12. There's not multiple ways you can do that. Any other outcome, like getting to where they sum to 3, you could get a 1 and a 2 or a 2 and a 1. Where they sum to 11, you can get a 5 and a 6 or a 6 and a 5. Here, there's only one unique way you can get a 2. There's only one unique way you can get a 12. Okay, in the box shown below, each ticket has 2 numbers. All right. For instance, the first number on this ticket is 3. The second number is 1. A ticket is drawn at random. Find the chance that the sum of the 2 numbers is 4. All right, so all we need to do here is just see. It's just like a counting problem here. So the total is, for the first ticket it's 3, for the second ticket it's 4, for the third ticket it's 4, for the fourth ticket it's 5. So if you draw a ticket at random, the chances that the sum of the 2 numbers on the ticket is 4 is 2 and 4, so 1 and 2. Okay? Now they ask the same question for these tickets here. So you have, this sums to 3, 4, and then 4. And then 4, then 5, then 6. So the chances that you pull a 4 here is 3 and 6, 1 and 2. Okay, now repeat for this last box. Okay. 3, 4, 4, 4, 4, 4. Yeah. 3, 4, 4, 4. And then 5, 6. Okay, so now it's 3 and 6 again, 1 and 2. The chances of that you pull a 4. And I think I messed up part B. Let's do part B again. With the chances of pulling a ticket that's a 4 in part B. So let's see. 3, 4, 4, 5. 6, 6. So there's only 2 4s. 2 of the 6 were 4s. So 1 and 3.